Vector-valued functions now is what we're talking about, you guys. The goal's to graph VVFs. I suppose that stands for vector-valued functions. That's number one. Goal number two, to generalize the ideas of limits and continuity to vector-valued functions. So the thing is, you already know what a vector-valued function is. Recall when you represent a curve parametrically, which you did in Calculus 2, using functions of, say, a parameter t, recall that the parametric equations x equals f of t and y equals g of t can, in fact, be used to represent a curve in the plane. You did it a lot in Calc 2. Now, we think of x and y then in terms of f of t and g of t. We think of that, we put those together and make what we call a vector out of them, and it'll be a vector-valued function. So r of t is how we represent the vector-valued function, r with a little half arrow over it. And then we could use component form notation. The first component would be f of t. The second component would be g of t. I was going to try to fit it in there, but if you like, you could, I'll fit it down here. If you like, you could use ij notation, r of t equals f of ti plus g of t j. Now, when we think of a set of parametric equations as a vector-valued function, it has to be true that the initial point of the vector is at the origin. It's at 0, 0. And we think of the vector as forming the curve by looking at the tips of the arrows. So we don't typically draw all the arrows associated with values that we get when we plug in t and get f of whatever t is, comma g of whatever t is. Usually we just think of the tip of the arrow as a point on the curve. And the domain would be the set of all allowable inputs. Set of all allowable inputs. The way I've written it here, all allowable values of t, the parameter. And I'll say more about the domain in just a little while. So you've already been introduced to one vector-valued function. So the parametric equations of a line in space, remember, x equals x naught plus at, y equals y naught plus bt, and z equals z naught plus ct. And what we're going to do in this section, if it's the equation or the parametric equations of a line, we're just going to put it in vector form so that the first component, x, the x component is going to be x naught plus at. Second component, y naught plus bt. Third component, z naught plus ct. And so what we're going to do is just write in a different sort of way, in a vector format, something you're already familiar with. So instead of thinking of this as a set of arrows, we're going to think of it as a set of tips of the arrows, a set of points. And so that particular vector-valued function is what we would call that, represents a line in space.